Hi, my name is Hassan Attarchi. I'm last year PhD student in mathematics at Georgia Institute of Technology. This work, why escape is faster than expected, is a joint work with my advisor, Professor Bunumovich. And in this work, we study escape rate of some open dynamical systems. Let's start with some definitions and notation about the open dynamical system. Let's T hat be a map from M hat to M hat which generates a dynamical system on phase space M hat and H be a subset of M hat. Then the open dynamical system corresponding to the map T hat with the whole H is defined by map T from M to M hat, where M is a complement of the set H in M hat. Uh, and the iteration of map T, to understand the iteration of map T, is enough to keep track of the iteration of the point x in M as long as they do not enter the whole H. Now it's time to have a few words about the escape rate. For any point x in M, the escape time is defined by the smallest natural number n such that nth iteration of t hat acting over x falls in holes h and is denoted by tau x. And also, with help of this escape time, we can define some subset of M, which is denoted by M to power n, and they are the subset of M which has all point of M with escape time bigger than n. Now let mu be a world probability measure on M, then upper and lower bound of the escape rate of the measure mu are defined respectively by lim sup and lim inf of 1 over n ln of mu mn when n approaches to infinity. And when these two values coincide, then we have the escape rate of the system. Also, there is an alternative definition of the escape rate, which we can have with some extra assumptions. And these assumptions are as follows. If t hat is a measurable map and h is a measurable set with respect to the Born measure mu, then the escape rate of mu is defined by simply negative limit of 1 over n ln of mu mn when n approaches to infinity with negative sign. And finally, we have to know about conditionally invariant measure. They are very important tools in studying some open dynamical systems and also evaluation of the escape rate. A Born measure mu is called conditionally invariant with respect to open dynamical system T if it satisfies the following equation for all Born set A in M. And it's interesting to know if mu is a conditionally invariant measure, then the escape rate of the system is defined as if we denote it by negative ln of lambda, then lambda gonna be mu of m1 or measure of set m1, which is equivalent to measure of set of all points which has escape time bigger than 1. And now it's time to talk a little about the estimation of the escape rate. First of all, the escape rate itself sometimes is hard to be evaluated and computed, and so we need lots of information, and therefore some mathematicians and physicians use the estimation of escape rate instead of the actual escape rate. And to have this definition of these three estimation, we need a setting for them. So let's consider we have a Markov partition E1 to Ek of the phase space M hat with element E1 to Ek, and all of them has a positive measure. Then TI be an open dynamical system with whole AI, and we assume TI admits an absolutely continuous conditionally invariant measure mu I such that its escape rate is well defined, and also we denote the set of all points that have not escaped after n iteration of map TI by MIN. So, with having this notation in mind, we can talk about the first estimation, here denoted by m1, and is defined by negative ln of 1 minus h, where h is 1 over k, or equivalent is the average of the whole sizes, and k here is the number of elements of the Markov partition. This type of estimation based on the assumption that the density of the absolute continuous conditionally invariant measure remains uniform inside the system, while the whole size we assume is 1 over k. And the other estimation here denoted by N2 is given by this formula, and this estimation is based on the assumption that the density of conditionally invariant measure is a constant inside of the phase space. And under this assumption, when the whole location is EI, when the EI is a whole, then the escape of the rate of the system is negative L of 1 minus HI, where HI is a measure of set EI, or measure of the size of hole. By taking the average of these values, or equivalently by taking the average of the estimation of escape rates for each position of the hole, we can have estimation N2. And finally, we have estimation N3 given by the following formula, and in this case, we assume that the density remains uniform in the system and the whole size is the average of 1 minus mu I mi1 with respect to the probability measure mu. And to let's see what does it mean, average of these values. I should remind you that at each iteration of the map Ti, the same portion 1 minus mu I mi1 of the remaining points of the phase space escape through the whole Ei with respect to absolutely continuous conditionally invariant measures mu I. Therefore, the average of these values is equivalent to average of the proportional leaks of the open dynamical systems Ti with respect to their absolutely continuous conditionally invariant measure mu i's. So now it's time to state or result of this work. First of all, if we had is a dynamical system from M hat to M hat with probability measure mu, and also we have a Markov partition with element E1 to EK, and open dynamical system Ti with the whole EI, all of them admit uh, absolutely continuous conditionally invariant measure. Then under all these assumptions, if we take the average of the actual escape rates of the system for different position of the hole as elements of the Markov partitions, it's going to be always greater than the naive estimation 3, N3. And that's the reason of that inequality is concavity of the function negative Ln, which appears in definition of the escape rate. And the final result is state that the estimation in N2 is greater than or equal to N1. These two estimations become equal when the elements of the partition have the same size, or all of them have the same size 1 over k. And finally, I can tell you I evaluated this estimation for 3 different examples in the original work on the skew 10 map, Arnold's cap map, and logistic map. And you can see some information about this estimation and calculation of this in these examples on the poster itself. Thank you for your attention.